myself, Bal Raj Deshwal. Well, I'm teaching chemistry back in India, and here I'm working as a visiting scientist in Korea Institute of Energy Research. Today in this spring meeting, my topic of discussion is absorption of SO2 from flue gas using PVDF hollow fiber membrane contactor. Friends, as you know, sulfur dioxide is most progressive air pollutant, and it has a hazardous effect on ecosystem and human health. It is main culprit which causes acid rain, which damages the vegetation, buildings, metal structure, monuments. So due to stringent regulations in the past years, it has become mandatory. It is the burgeoning need of the time to remove SO2 from the flue gas and other industrial gas streams. The major sources of SOx, as you know, the main natural source of SOx emission is the volcanic eruption, which contributes about more than 50% of SO2 in the group. And other sources of SO2 emissions are the combustion of fossil fuel, particularly the power plants, petrochemicals, combustors, and incinerators. Now, let us have a look on the conventional processes for the flue gas desulfurization, FGD. FGD is presently the state-of-the-art technology for removal of SO2 from the flue gas and other gas streams. And it has achieved about 95% SO2 removal efficiency. And the beauty is, the products of this FGD process are reusable, and the reagents used in FGD are quite readily available, and they are cheaper too. But on the other side, it has some limitations, like it requires high capital cost, larger space, corrosion, some operational problems like flooding, foaming, entrainment, and disposal of byproducts also increases the cost, scaling and deposit of the solid on the absorber and the downstream equipment. So, another technology, the potential technology for removal of the acidic gases is the hollow fiber membrane contactor. This is a potential emerging technology these days. Hollow fiber membrane contactor is a device which allows gas-liquid, liquid-liquid mass transfer without dispersion of one phase into another. Let us have a look on the advantages of membrane gas absorption process. It has operational flexibility, independent gas and liquid flow rate, large interfacial area, compact size, linear scalar. Modular design allow to work in the wide range of capacities. Interfacial area is known, so it helps to predict the performance of the reactor. If we see the size, if we compare the size, MGA process allows to reduce about 10-fold reduction in the size of the reactor. So, of course, it has a lot of advantages over the conventional processes. And this technology has been used successfully in various fields, like fermentation, pharmaceuticals, wastewater treatment is one of the most important applications, chiral separation, semiconductor manufacturing, carbonation of beverages, metal ion extraction, protein extraction, and the last but not least, these days in the preliminary stage of course, but it is used for the removal of CO, CO2, H2S, ammonia, methane, and several acidic gases from the flue gas streams. So the objective of the present study, my study, is to prepare a suitable hollow fiber membrane and characterization of that membrane, and further utilization of that membrane for removal of SO2 from the flue gas. The most common polymeric materials used for hollow fiber membranes, these are propylene, polypropylene, polysulfone, polyether sulfone, PTFE, and PVDF. Among these polymeric materials, PVDF has attracted quite remarkable attention in the past years because of its unique properties. It is quite stable thermally, it possesses very good chemical resistant to most of the corrosive chemicals, and thus it is ideal for use in the abrasive environment. So I selected PVDF, the polymeric base material, for preparation of membrane. This is the flow sheet diagram of preparation of hollow fiber membrane. PVDF and NMP is a solvent here. They were mixed in the ratio of 1:4. NMP was taken in the flask and then suitable amount of PVDF was added into it. They were mixed thoroughly at 60 degrees centigrade for 24 hours to ensure the complete dissolution. Then they are filtered using glass filter and degassing is done using ultrasonic vibrator. After degassing, spinning is done. Spinning is done by wet phase inversion method and it resulted into formation of hollow fiber membrane. These are the spinning conditions of hollow fiber. The depth was kept 20. Water was used as internal as well as external coagulant and temperature was kept about 15 degrees centigrade. This is the schematic diagram of the wet phase inversion method, a versatile method for preparation of the hollow fiber membrane. Dope solution was taken in the steel container and it was pressurized using nitrogen gas. The pressure of nitrogen gas was kept between 3 to 5 atm. Internal coagulant, that is water, was kept in another container and they were both pressurized through the tube in orifice spinneret. After passing through this spinneret, the hollow fiber membrane, it was coagulated, it was solidified in the external coagulant. Water was used as external coagulant. Thereafter, the hollow fiber membrane was washed thoroughly and it was wound up around the wind-up drum. This is the morphology of the PVDF hollow fiber membrane. These are SEM micrographs. This is the overall cross-section. If you look at clearly, the inner and the outer layer of the hollow fiber membrane, they contains finger-like structure, because in our case we have used water as internal as well as external coagulant. So rapid precipitation occurred on the outer and the inner wall and it resulted into the finger-like structure. You can see the large microvires on the inner side of the wall. In the middle there, the sponge-like structure is obtained, and this is of course due to slow precipitation because it does not allow the water to enter much inside the membrane. Now this membrane was characterized using gas permeation method. The permeability of a gas across the membrane is a combination of Boisseville flue and the Knudsen flue. So J is the permeability, of course. It's a combination of two terms. So this equation can be written in the simplified form. Here the permeability was plotted against the mean pressure Pm, and from that we determined the intercept I0 and the slope. Using this intercept and slope, we determined the mean pore radius R and the effective surface porosity using these two equations. The mass transfer in the gas-liquid contactor occur via diffusion across the membrane, and for a non-wetted membrane, assuming that the pores of the membrane are filled with gas, so the overall mass transfer coefficient is a combination of three terms. This is the gas phase mass transfer coefficient, membrane coefficient, and of course the liquid phase mass transfer coefficient. If you see here, this is a membrane, and the pores of membrane are filled with gas. On the lumen side we have passed the gas, and on the cell side we have passed the absorbent solution. And since the absorbent is quite reactive, the reaction between SO2 and absorbent is very rapid reaction. That is why the contribution of third term can be neglected, so equation becomes quite simplified. Now, the membrane coefficient of the prepared PVDF membrane was determined using gas permeation method as well as using the experimental absorption method. For a non-wetted membrane, the membrane coefficient can be calculated from the gas permeation data. Here dA, this is the diffusivity of gas, multiplied by the effective surface porosity. And here this diffusivity is a combination of continuum and Knudsen diffusing, because in our case the size of the pore is greater than 1 micrometer, so the contribution of second term is neglected. So directly we can find the diffusivity multiplied by the gas permission data, we can find the membrane coefficient. And this membrane coefficient from this gas permission data was found to be 1.266 10 power minus 3 meter per second. When we determined the membrane coefficient using the gas absorption data, it was found little higher than that. So this higher value of membrane coefficient from the gas absorption data indicate the partial wetting of the hollow fiber membrane, and wetting is the basic problem because this study, the absorption of acidic gases using membrane, this is in the preliminary stage, and this wetting of membrane is the basic problem these days which must be dealt with in future. So using that hollow fiber membrane, we have prepared a module. The inner diameter of module was 1 centimeter. Module length is about 15 centimeter. These are the hollow fiber inner and outer diameter. We have used total 20 hollow fiber in each module, and we have used 3 modules in a series. This is the effective fiber length, 12.5 centimeter for each module. We have used 3 modules. So these are few important characteristics, specifications of the module we have used for removal of SO2 from flue gas. These are the experimental conditions. We have used water, sodium sulfite, sodium carbonate, sodium bicarbonate, and sodium hydroxide as the absorbent for removal of SO2 gas. Keeping in mind that SO2 is acidic gas, so we have used most of the alkaline reagents here. Inlet SO2 was varied from 200 to 2000 ppm. These are the gas flow rate, liquid flow rate. This is the schematic diagram of the experimental setup. SO2 was mixed with nitrogen and then passed through these hollow fiber membrane module. 3 modules were used in a series. Now these are few equations to determine the overall mass transfer coefficient, SO2 removal efficiency, and the rate of SO2 absorption in the module. Now the first operating variable was the liquid flow rate. Liquid flow rate was changed from 1 to 15, about 14 milliliter per minute. And it was observed that SO2 removal efficiency increased sharply in the beginning and then attained a steady state. The sharp increase in the beginning is of course because at low liquid flow rate, the NaOH available for complete reaction with SO2 was not sufficient. That is why this removal efficiency increased in the beginning, and then of course it attained a steady state at a suitable liquid flow rate. The another factor we studied the effect of inlet SO2 concentration on SO2 removal efficiency. SO2 removal efficiency decreased slowly with the increasing concentration of SO2. It occurred because we have carried out this study at a fixed liquid flow rate, and the increasing concentration of SO2 required larger and larger amount of NaOH, but the concentration of and the liquid flow rate of NaOH was fixed. So it is obvious that SO2 removal efficiency will decrease. So this is the expected result. Now this is the effect of gas flow rate on the SO2 removal efficiency. Gas flow rate changed from 2 to 16, about 15 liter per minute. SO2 removal efficiency decreased with the increasing gas flow rate, and it is due to at high gas flow rate the residence time of the gas was quite low. In our case we have calculated the residence time of the gas. The maximum residence time was 0.11 second. However, it decreased about 5 times at gas flow rate of 40 milliliter per minute. So due to low residence time, this rate of diffusion decreased sharply, and this occurred in the lesser SO2 removal efficiency. Now we have plotted Sherwood number and Graves number. Graves number of course is the gas velocity, and this is the overall mass transfer coefficient. The gas velocity was varied from 0.2 to approximately 1.7 liter per minute. And it was found that the gas velocity has a negligible effect on the overall mass transfer coefficient. So from this straight line, from the intercept of this straight line, we have determined the membrane coefficient using this experimental data. As I told you earlier, it was found a little higher than the value obtained from the gas formation data. Now we have studied the effect of concentration. We have selected the NaOH as the absorbent and increased the concentration from 0.01 to 2 molar. And of course, there was increase in the SO2 removal efficiency with the increase in concentration. From this figure, it is quite obvious, it is very easy to determine the optimum liquid flow rate and the optimum concentration to be used for the SO2 removal. We have used several absorbents for removal of SO2. We have selected NaOH, sodium sulfide, sodium carbonate, and sodium bicarbonate. Among these absorbents, sodium carbonate proved to be the best absorbent for SO2 removal. Now, in brief, it can be concluded that the hollow fiber membrane which we have prepared, it has quite integrated asymmetric structure. There were the large macrovide on the inner side and the finger-like structure on the outer wall, and there was spongy structure in the middle layer of this hollow fiber membrane. We have achieved about 85% efficiency using 2 molar NaOH in the hollow fiber module. We have investigated the effect of several variables, and it was found to be quite promising technology for removal of this acidic gas. Though this technology, membrane gas absorption process, it is in the preliminary stage, it has several problems yet which must be dealt with in future, like the fouling, wetting, disintegration. These are some common problems which must be considered, and of course some of the researchers have proposed some techniques to increase the hydrophobicity, the stability of membranes. So these are some issues which must be dealt with in future. Thank you very much.